In this video, I will discuss the solutions to the workshop on torques and static equilibrium. When solving problems involving static equilibrium, these 5 steps outline the important problem-solving strategy. We will apply this problem-solving strategy as we go through the solutions to the questions. So the first question looks at a pole vaulter at the start of his run, and the pole vaulter is holding a pole as shown in the figure below. So the figure actually already gives you the free body diagram. The free body diagram here on the right is the usual free body diagram that we usually draw when looking at forces and applying Newton's laws of motion. But when we are talking about torques, the position of the force is also important. And so when you draw the free body diagram in torque problems, this here will be the more appropriate free body diagram. We can see 3 forces. One force exerted by the pole vaulter's right hand, and that force is directed downwards. We have the force exerted by the pole vaulter's left hand, and that is directed upwards. And we have the force acting on the pole. And the weight force always acts at the center of mass or center of gravity, and that is at the geometric center of the pole. So meaning at the middle of the pole, you have this weight force that's moving downwards. Now, as I've mentioned earlier, the position of these forces are important. And so just looking now at the free body diagram on the left, we identify the lever arms. The lever arm is the distance between the force to the pivot point, and that would be perpendicular to the force. So before we can identify the lever arm, we should first identify the pivot point, or the point about which the pole will rotate if there is an unbalanced force. The choice of pivot is arbitrary. It's up to you to choose which point you'll put your pivot point at. The tip here is to put the pivot point at the location of an unknown force. In that case, the torque will be 0 at that force, and therefore that eliminates one of the unknowns. Or put the pivot point at the point where there are a lot of forces that are acting. So here, in our free body diagram, we have 3 forces, Fr, Fl, and weight, W. A smart choice for the pivot point would be to put it at one of the forces that we don't know. So we are given the mass of the pole, which means that we can get the weight of the pole, because weight is just equal to mass times gravitational acceleration. And since the mass of the pole is given, then we know what the weight of the pole is. So we should not put the pivot point at the position of the weight force, because we know the weight force. Now the force on the left hand and the force on the right hand, we don't know either of those forces. In fact, we are being asked to find what's the force exerted by the left hand, Fl. So we can either put our pivot point at Fr or at Fl. If I put the pivot point at Fl, then that would eliminate Fl, and we will be able to solve for Fr, after which we can solve for Fl. Or I can put the pivot point at Fr and solve the torques about the pivot point at Fr. By doing so, I eliminate Fr, which is one of the unknowns, and that will allow me to solve for Fl, the other unknown. Right, so once we've identified our pivot point, we identify our lever arms. So the lever arm is the distance between the force to the pivot point, but it's the perpendicular distance from the force to the pivot point. So we're given in the problem that the pole vaulter's left hand and right hands are 0.9 meters apart. So we're given the distance between the left hand and the right hand, okay, 0.9 meters apart. Right, we are also given that the pole center of mass is 0.9 meters from the pole vaulter's left hand. So that means that this distance here, sorry, 1.2 meters apart. So the lever arm is the distance between the weight force and the pivot point that we've chosen. So the lever arm between the weight force and the pivot point will be 1.2 meters plus 0.9 meters, which is 2.1 meters. Right, so now we know the pivot point and we know the lever arms. We can then solve for the net torque. And we want the pole to be in equilibrium. So we want to impose the condition that the net torque is equal to 0. Okay. So we consider each of the forces relative to the pivot point. So first, FL, the force FL. Torque is equal to the lever arm multiplied with the force. Okay. So looking at the force FL, the lever arm is 0.9 meters. So that will be 0.9 multiplied with the force FL, which we do not know, so we just leave that as FL. Okay, now the torque produced by FL will be positive because the tendency of FL is to rotate the pole in this direction, which is anticlockwise, and anticlockwise gives us a positive torque. Okay. So the sign for the torque due to FL will be positive. So I'll leave it as 0.9 times FL. Now that we've determined the torque due to FL, let's determine the torque due to the weight. So again, torque is equal to lever arm, which is 2.1 meters, the distance between the weight force and our chosen pivot point. So that will be 2.1 multiplied with the weight force. Right, now next determine the sign of the torque. The tendency of this weight force is to pull the pole in a clockwise direction. Okay. Pull the pole downwards, causing it to rotate in a clockwise direction relative to the pivot point. And we've said that a clockwise rotation gives us a negative torque. Therefore, the torque due to the weight force will be a negative 2.1 multiplied by the weight force. Right, so those are the only two forces about the pivot point. The torque due to the right hand will be equal to 0 because we've put our pivot point exactly at the position of that force on the right hand. So it's just 0.9 multiplied with the force by the left hand minus 2.1 multiplied by the weight force, and that whole thing is the net force, and it's equal to 0. We now rearrange this equation to isolate the unknown FL, the force on the left hand. So adding both sides with 2.1 times weight, we have 0.9 FL, 2.1 W. Now dividing both sides by 0.9 gives us the isolated FL, which is equal to 2.1 W divided by 0.9. W, we know, is the weight force, which is mass times gravitational acceleration. So we have 2.1 times the mass, 5 kilograms, times the gravitational acceleration, 9.8 divided by 0.9. So plugging everything in the calculator, we get a force on the left hand of 114 newtons. If we wanted to find the force on the right hand, then we can just do sum of forces is equal to 0. Or you can also do net torque is equal to 0, putting your pivot at the left hand. But going just a step further, it's not in the question, but for example, you wanted to find FR. You can just do net force is equal to 0. You have two forces that are pointing downwards, FR and W. So those should add up, and that should be equal to FL. So FR, the force on the right hand, will now be FL minus W. So this is how you get the force on the right hand.